Okay, so this is the second chapter on equilibrium. The first one covered generic equilibrium, and it was the longest one. This one will not be as long, although it's got more to it than the third one, which we're just going to do on solubility. This has got a fair amount to it, but if you understood, if you did okay in the last one, and even if you didn't, it'll all make more sense because actually, these turn out to be, by the time we get to the K problems, the actual problems with KC, we're going to call them KA and KB, they actually turn out to be easier in a lot of ways than the other ones were. And you'll see why, even starting today, when I derive what's called KW. Okay? And that's what we have to do first. We have to talk about the fact that water, by itself, with nothing added to it, not an acid or base added to it, water by himself ionizes into hydronium and hydroxide ions. So what am I drinking in here? Water. You hope it's water. And if it is, I'm drinking a little bit
Appletini.
My appletini, a little bit of appletini, but mostly I'm drinking a little bit of hydronium hydroxide ions along with that water. All right, because every now and then a water molecule bangs into another water molecule, and it does this. It turns into hydronium and hydroxide ions. Now, it doesn't taste sour, and it doesn't taste bitter. Water doesn't, because water is neutral. We all know water is neutral. Why is it neutral? Well, because I said it is, exactly.
Water plus water.
Well, take a look over here. For every hydronium ion I make, I'm also making one hydroxide ion, right? In order for something to be acidic or basic, as you know from Chem 1, I would have to have more hydronium ions to make it acidic. I would have to have more hydroxide ions than hydronium ions to make it basic. That's the point, all right? And if something were basic, I would know it because it would taste bitter. And if something were acidic, I would know it because it would taste sour. All right. And that's all from Chem 1 stuff. But now, I'm going into Chem 2 from here. We did a whole review last period, and what I just said up here really isn't that much more than a review. But what I'm going to do now is going to be putting together what we learned about Kc from last chapter with this particular equation. Look at it. If this had said this is one little thing different. If this equation had been, the question I asked you, the very last question on the test, was this. Derive the equilibrium constant given AA plus BB yields CC plus DD. Now, the vast majority of you did not do that because you didn't bother to study it. I understand that. A handful of you did. But a handful of you did. Most of you did not. All right? But you may remember the very first day of the equilibrium chapter, the first equilibrium chapter, I derived Kc from this. Okay? Now, I'm doing a specific equation, water, ionizing into hydronium and hydroxide ions. And I'm going to do the same exact thing for it. Watch. If I assume that the rate forward would be that reaction, a one-step mechanism, it would be that reaction because the coefficients would be 1. If I assume a one-step mechanism, the rate forward would be Kf times the reactants. The rate reverse would be Kr times the reactants, times the products, I should say. That is from kinetics. That goes way back to kinetics. It's amazing how many things we've used and reused and come back to in these first, these 3 topics: thermodynamics, kinetics, and equilibrium. At the end of equilibrium, last chapter, what do? We went all the way back to delta G. All right, we got all the way back to that and tied it all together. Well, this is going back to the kinetics chapter. Everybody would remember, I would hope, that that's what you would have written for the rate law expression in the forward direction, the rate law expression for the reverse direction. Of course, at equilibrium, what do we know about those two? At equilibrium, the forward rate's equal to the reverse rate. So, Kf times water. Where did water squared come from? Yeah, it's water times water. So, Kf times water squared equals Kr times hydronium and hydroxide. All right, so all I'm doing is deriving Kc into the ground. Deriving Kc, right? Yeah. All I'm doing is deriving Kc again. Only when I get there, you're going to see something a little bit different about this particular reaction. I couldn't do it a generic A, B, B, C, C reaction because it's not always the case. It will be the case in this reaction, and it's really important that we know how to use this because this particular reaction, all right, and the variations on it when I add an acid and a base to it are what we're going to use to determine pH, hydronium, and hydroxide ion concentration. That's what the pH basically is concerned with. All right? So, how acidic or basic a solution is. So, if I rearrange and bring all my constants over, it's nothing here. If you wanted full credit for your last test, this is what you should have put, only instead of the hydronium, it should have been C and D. Raised to the C power, raised to the D power. Okay?
Can we get either test back? Well, not back, but
I have your grades if you haven't seen them. They've been graded for a while. They've been on Skyward for a while. Okay, so you all know what KF over KR is. It's the ratio of the forward and reverse rates, constants here, and that is KC. Okay, and we use KC. We calculated KC, and we determined how the size of KC would affect the reaction. All of that was last chapter. It hasn't gone away. If you didn't do it then, if you weren't able to do it then, you better know how to do it for this one because it's going to be here again. Only it's going to be a little bit easier in this case. Let me show you why. If I assume I have a very dilute solution, if I have a dilute solution, I'm not going to get a whole heck of a lot. Matter of fact, you want to know how small amount I'm going to get? If I have no acid or base at all in this stuff, just sitting there, and I'm going to say this in a few minutes down here a little further, I will have that many moles per liter of hydronium ions. That's how small amount of hydronium ions I get. Now I have the exact same number of hydroxide ions. It's a really small amount. So basically, for all intents and purposes, the amount of water stays constant. In dilute solutions, the water concentration is virtually constant for a couple of reasons. All right, first of all, if it's a dilute solution, there's not much of the acid added to it. And secondly, we're going to be talking about weak acids here, which don't totally dissolve in solution anyway. So for both of those reasons, as you'll see, water is virtually a constant. So guess what I'm going to do? I'm going to bring that water over to where the other constant is. I'm going to call it Kc times water squared. Now, what that does for me, as you can probably see, is makes a much easier equation to work with here. I don't have a denominator anymore, do I? Yeah, that's nice, because this new constant here, this new Kc water squared thing, he is our constant called Kw, or the ion product constant of water. Kw equals hydronium times hydroxide. Maybe some of you even remember my little pun on Kw from last year. When there's trouble, you call Kw. Remember that?
No.
Well, we did it. We actually did it when we were calculating acids and bases. I realized it was one of the last things we covered at the end of the year, and you were sleeping. But we are going back to that right now, because that's what Kw is. He is the ion product constant of water. Now, look what I've done there. Almost all of this, from here down to here, until I get to this sentence, was what you would have done anyway to derive Kc. It's one of the reasons why I told you I was going to make you do a derivation on the last test, and I told you what that derivation would be, because I knew we were going to see it again. There's Kw. That's what he is. And the fact is, I can tell you exactly what Kw is. It's a constant, so it doesn't change. If there's information I can give you to calculate it, it will always be that constant at a particular temperature. And there is information I can give you. I can tell you that and this just continues, this is not a new topic, I just didn't have room on the board. At 25 degrees Celsius, if you have pure water, the hydronium and the hydroxide ion concentrations, aside from being equal to themselves, which of course they are, equal 1 times 10 to the negative 7th moles per liter. That's how many, like I said a minute ago, 0.0000001 moles per liter. It's a really small number, but it's able to help us get Kw. Because if I know the hydronium and hydroxide are that number each, apiece, can't I solve for Kw? Sure. Kw is going to equal hydronium times hydroxide. Right? I'll plug in my numbers. It's going to equal 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. I think everybody can do that in their heads. What's that going to be? 1 times 10 to the negative 14th. And that's what Kw is and will always be, assuming the temperature is 25 degrees. So here's why that helps me. Kw has to be that number. He's constant. Constant doesn't change. If I change the hydronium by adding an acid, or if I change the hydroxide by adding a base, what must happen is, what? If I make this guy bigger, what must happen? to this guy. He must be what? Smaller. Yeah. And you notice something about what the where I'm going with this. I'm going to eventually get there in a few seconds about pH. What do you think pH is? Yeah, it has something to do with logs. It has something to do with powers. Okay? Because what is neutral on the pH scale? Ah, there he is. Right there. That's 7. Yeah. Mm-hmm. So, and that's what we're going to talk about. The actual way we measure pH, all right, created by a guy who simply didn't want to write down the actual concentrations. He said, let's just write down the powers. It's a lot easier. And that's what they did. So pH is what I'm going to talk about next. I'm going to use that to be able to calculate the hydronium, hydroxide, and the pH. Now, pH is small p, capital H. Big P, little h is...
Funny.
Just ask Mr. Phillips. Mr. pH Phillips. Okay. pH is, and here's a nice big long fancy definition, but in reality it just means the power of 10 in the exponent, or in the hydronium ion concentration, okay? It's the power of 10. So it's a negative common logarithm of the hydronium ion concentration. I mean, that sounds impressive, but it really isn't that difficult. Well, it's going to be easier this time.
Yeah, it does, actually.
So basically, all we're going to do is just write down the absolute value of the power of 10 in the hydronium concentration. That's what we're talking about, the power of 10 in the hydronium. We're going to take the negative of that, not absolute value, the negative of that number. So if you just look at the exponent, you can pretty much tell. Okay. Now, I was amazed last period. I decided, well, just for fun, I don't even have this written down in my notes. I'll just make sure you guys know what logs are. Okay? So I decided, okay, I'll do that. So let's see if I do that with you guys, if you can figure this out. Okay? Do not write these down. Just some examples. What was the log of 10 to the third power? 3. Everybody agree it's 3? Okay. What's the log of 100? 2, right? Because what is 100 in exponential notation? 10 squared, right? What's the log of 0.001? -3, right? Right? Okay. So, and basically, log is just the power. The reason this guy would be -3 because 0.001 will be 10 to the negative third, right? So a log is just the power to which 10 is raised. Okay. And if we're taking the negative of that, it's going to be we're going to have to do that in our calculations. The power is 10 to the negative third by pH would be 3. That's all you got to do. It's that simple. What's that? Okay. So let us do a couple of problems. Oh, well, here, just write that. That's your actual equation down, real quick. That's what you'll be writing down for your equation. By the way, that equation is on your formula sheet that you'll get to use on the AP.
Wow, this is so hard back in Chem 1. Now it's easy.
Well, that part of the reason it's easy, I should go back to this and show you something about why this is easier. Okay? Let me show you. In Chem 1, that's all I gave you. We did not do equilibrium. We had never seen equilibrium. So I just said, hey, you got to have it on faith. You got to take my word for it that there's this relationship between hydronium and hydroxide, and it has to do with this KW. And I never, but if you think about it, we have been doing this for the past, starting here in kinetics chapter, and then a whole, month and a half of doing equilibrium problems. So it should make more sense to us now. Okay? I would hope. All right, let's get to the problems. Copy this example down. I'm going to eventually get to, but it's going slowly. And we're going to do 2 problems on the board. And then you'll have some homework. Come on, one more. Last one. There you go. All right, copy this guy down. Oh, wait, I didn't. That whole board's yet coming. Sorry. Shouldn't have gone back that far.
Yeah. What were you doing?
What was I thinking? All right.
We're going to have to cut this out.
There we go. There's my example. I made this first one really, really easy.
The answer's 12. Actually,
Actually, it's a funny thing.
The answer is 12.
Oh, wait, hold on. My fault, my fault.
What?
Stop, stop, stop.
No, but I already.
You should put forward, I want to put this as different kind of calculation. Roman numeral 3, strong acids. Ionized completely in solution. That came up out of order. My fault. Okay? And then we'll copy the example then. We're going to talk first about strong acids and bases. I know it's kind of crazy because this whole chapter, the reason we're doing this in Chem 2, is we're talking about equilibrium reactions. Why am I going to start by talking about non-equilibrium reactions? All right, that's what I'm going to do. I'm going to start talking about these. Well, first of all, it will be easier, and you will definitely have problems like this on both my test and the AP. Secondly, you've already seen it. You actually did these problems, these kind of problems, last year under the acids and base chapter. I know you don't remember it, and that's okay, but we're going to go over it from scratch here. Again, pretty much most of all of what we did for these first two periods were review. The difference is you should understand it better having the background in equilibrium that you did not have when you did acids and bases originally. Because all we at that point had was solution. We knew about solutions, and we knew about phase changes, equilibrium, but we had no idea about concentration, real equilibrium. And after you all copy that down, I'll show you what I mean. When I start to do this problem. First of all, can anyone tell me the answer to the pH of this solution? pH is going to be 3. My answer is going to be 3. Everybody is another example of how if you get a multiple choice. I was looking yesterday I was looking at like just test taking stuff because we had this long weekend and I was looking over some of that stuff for the AP. You have 90 minutes to take 60 multiple choice questions. Okay, think about that. 90 minutes, 60 multiple choice questions on the AP, right? Can you spend, like what I'm going to do to show you how to do this problem, can we afford to do that for every problem? Absolutely not. For the free response questions, you do need to show the work like I'm going to show you here. But for some of them, you got to use your head. You got to use your common sense. You could see the concentration. You could see he's a single monoprotic acid, HCl. You know, I tell you he's a strong acid. That means it breaks up completely in solution. So that concentration is the concentration of the hydronium ion, and therefore, that's times 10 to the negative third, pH would be 3. And that's how you would figure that out. All right, but I'm going to show you how you would do it, because what could I do to make this much harder? I could have an uglier number, okay? I could have an uglier acid, all right? I could have a base instead of an acid. I'm going to do that in my next example. And I could have not a monoprotic, but diprotic or even dihydroxide, a base, or a diprotic acid. And all of that stuff would make a difference in how you would do the calculation. But for a simple one like this, you should be able to tell me it's 3. The answer is 3. However, here's what you need to show me on my test, so I give you partial credit, and what you'd have to do if you were doing this as a long, free response kind of question. You would show the equation. What is the equation? How is HCl going to react with water? It's going to be, it's going to be HCl plus H2O yields what? What is HCl plus H2O going to give me? H3O, hydronium ions, plus Cl negative. And by the way, if you were to put, and you should, all right, and certainly the book will, HCl is a gas, H2O is a liquid, he is aqueous, and he is aqueous. But, I mean, that's not a big deal for me. I wouldn't be looking for that necessarily. In this case, there are times when you really, really have to put down AQSL when you do a precipitation. We're going to be talking about that in the solubility one next. All right, now here's what I need. Do not write what I'm about to write down. It's very important. Olivia, listen to this. Don't write it. If this were an equilibrium problem, okay, if this were an equilibrium problem, you would do this. ICE, right? And you would say, okay, my initial concentration is I put in 0.00100 molar, right? And then somewhere down here, for my I want you got to listen. Just because I said don't copy doesn't mean you can't listen to this. This is very important. It's the difference between strong acids and bases and equilibrium problems. This was an equilibrium problem last chapter. We are going to be doing this for weak acids and weak bases. You would have had like, okay, somehow or other you're told that the concentration of hydronium is 1 times 10 to the negative 8th molar at whatever. I'm just saying, you're making up these numbers. I'm making up numbers here. It wouldn't be 8th because that would make it not even an acid anymore. But my point is, you would have to do minus x, and do all that stuff. Why don't I have to do that? Why am I going to erase all of this nonsense? What does it being a strong acid mean? It's not an equilibrium problem. There's no backwards reaction. It doesn't exist. It goes 100% to completion. So if I put in 0.001 moles of this, how many moles of hydronium do I get at equilibrium?
0.0010 mole.
That's all I need to know. That's what I'm trying to get across to you. Okay? Erase all this here. I don't need to do ICE. If I'm given that concentration of that strong acid, he breaks up 100%. He will form the same concentration of hydronium, and of course, it's going to be the same amount. The series. It's going to be the same amount of Cl ions. Do I care about the Cl ions? No, I couldn't care less. I care about the hydronium because he's what makes something acidic or basic. All right, so I now know one answer. It asked me for 4 things. I now know this one, the hydronium ion concentration is 0.00100 mole. Got it? And I know that just because he's a strong acid, and that was the concentration I was given. And therefore, he breaks up completely in solution and forms that. Now, here comes the next question. When I need to find out how much hydroxide I've got. How am I going to do that? Might say we're in trouble. When there's trouble,
KW.
call KW. That's right. Yeah, very good. KW relates hydronium and hydroxide together. KW equals hydronium times hydroxide. Okay? Do I know KW? Yeah, sure. Do I know hydronium? Yeah. So what's hydroxide going to be? Just going to be hydroxide is going to equal Kw over hydronium. Everybody agree? All I did was rearrange the equation. Does that look good there, buddy? What was Kw again? 1 times 10 to the negative 14th molar squared. By the way, don't let that 1 limit your significant figures, okay? I'm just assuming that's the exact perfect number. Don't let him limit you. Hydronium, 0.00100 molar is going to be the hydroxide. Do I need a calculator for this? Absolutely not. What is 0.001? 10 to the negative third, right? This is 10 to the negative 14th. What's hydroxide going to be? 1 times 10 to the negative 11th molar. Molar cancels the molar square, gets your molar, right? Piece of cake. So I now know the hydroxide ion concentration as well as the hydronium ion concentration. I'm halfway done. All I got to get now is the pH and the pOH. Yeah.
Let's say next. I think it's 14. Yeah.
Negative 14. That's the constant. Okay. So the pH equals negative log of the hydronium, right? Okay. pH equals negative log of hydronium. I know the hydronium. Which one's the hydronium again? 0.001. So let's just call 1 times 10 to the negative third. Isn't that the same thing as 0.001, right? And it makes it easier for me to see it. So what's the negative log of 1 times 10 to the negative third? Yeah, pH is going to be 3. pOH. Great. I want you to realize something. pOH is going to be the same thing as pH, only using the OH concentration. But you don't need to do it. You will not need to do it. What would the pOH equal? It would be pOH equals the negative log of the hydroxide, correct? But what's it have to be? It has to be 11. Okay, it has to be 11 for 2 reasons. You can say, well, because that's 11. What's the other reason? They have to add up to 14. So the pOH, if you get whichever one you get first, you can always tell the other one by simply subtracting 14 minus the other one, the one you've already got. So the pOH will be 11.
Is it ever possible to have one of them be at 14, or is that?
Well, that's an interesting thing. The fact is, your question is about what happen. Can we have numbers, for example, that what happens if the concentration's over a point? I guess it's 2.7. What's the log of that? It's not going to be even a negative number, is it? Fact is, pHs only apply. The scale, the pH scale, only really is calculated for dilute solutions. Solutions that are somewhere between like 2 and 13. Once you get below that or above that, because remember this is a logarithmic scale, right? So when you get down close to either end of that, things go a little crazy. And you really can't calculate it accurately using the pH formula. All right? I'm not even exactly sure why. I just know that that's the case. It only applies to dilute solutions. Okay? So you're only going to have dilute solutions, yes. Okay, good enough. That's not, hey, we're not done though. That was one. How can I make this harder? I told you it's a long class. How did I say we can make this harder? I said I could give you uglier numbers. I said I could give you a base. I said I could even give you a different number of ions in that base. Look at that. That's got everything in it. I can't do this one in my head. I'm going to have to do this one the same way. Obviously, I did the last one the same way. But, I mean, the other one, I could have done that one in my head. I can't, really.
I know, it's awful.
I mean, I can make a legitimate guess about it. All right? I can make a guess about it, but I don't want to have to do that right now. I'll show you later how I can do that. But right now, let's just do this the same tedious way of showing me all the work, because this is how you get your points in the test anyway. And there's another problem with this guy too. You know what? He's a base and not an acid. Bases, when you put them in water, they don't really react with the water. What do? They just separate. They just dissolve or ionize in the water. And and I should also say this too. If you were to look at your formula for on your formula sheet, you don't have to. It doesn't actually say pH equals negative log of the hydronium. It says pH equals negative log of the H plus ion concentration. Okay? I could have done the acids like that too. HCl simply breaking up into H plus and Cl negative, aqueous, leaving water out of it. I could have done that. I don't, because I know coming up real soon is going to be where you have to show the equation of water because it's a reversible reaction, and I want to make sure you understand that. But that is actually the formula you get in your formula card. So it's the same thing. H plus and H3O plus is the same thing. They're the same. It's just one's assuming this breaks up like this for an acid. The other one assumes it reacts with water. This guy, for bases, there's only one way to really write it. CaOH2. Breaking up solid, breaking up in water into calcium ions, aqueous, and hydroxide ions, aqueous. But I got a problem with this, don't I? Is it balanced? It does matter.
Now you gotta put 2 OH.
Yeah, I got to put a 2 in front of my OH over there. And that will make a difference, as you'll see in a second. And we are going to have to use our calculators on this guy. Yeah. So if I'm given 0.0032 molar of that, I will get, for the calcium ion, although I couldn't care less, 0.00320 molar of calcium. I really don't care about that. What do I care about? I'm going to get 2 times 0.0032 molar. You see, I've got to multiply him by 2. I get twice as much. Hydroxide ion, so that's going to be 0.00640 molar for the OH concentration. So, hey, but you know what? We got a couple of changes already. Let's see what the change has been so far. Calcium hydroxide is a base, so he breaks up in solution into calcium and hydroxide ions. Calcium hydroxide had 2 OHs, so I have to put a 2 in front of there and therefore multiply the concentration by 2. And finally, my first thing I got last time with my acid was hydronium ion concentration. The first one I've got now is hydroxide. So my OH concentration is 0.00640 molar. Okay? Because he's a base. I mean, you can see it. When you draw it out, you can see that that's the concentration of the hydroxide. That's why I want you to do this. what do I do now that I'm in trouble?
KW.
Yeah. When there's trouble yet, call KW equals hydronium times hydroxide.
I really wish there was a surprise slide.
Okay? So I rearrange it, this time solving for whom? For the hydronium, right? See why I got to solve for the hydronium. I know the hydroxide's this. And Kw is 1 times 10 to the negative 14 molar squared. The hydroxide is 0.00640 molar. So now I need calculators. You have to look them up for me. What's the hydronium ion concentration in this case? Because I can't do that in my head.
Magic.
Anybody?
Magic.
What is it?
1.563.
1.56 times 10 to the what?
Negative 12.
Negative 12 molar. That look good there, buddy? There's your hydronium. Okay. Now, look at this part. As easy as the last one was, it was only easy because the numbers were easy and I really didn't need a calculator. This is exactly, you notice these are the exact same steps. pH is going to be what you'd expect pH to be, negative log of the hydronium, which is the negative log of 1.56 times 10 to the negative 12 molar. Now, you know the pH is going to be around 12, but it's not going to be exactly 12 because this number is not a 1 in front of it, is it? So, get it on your calculator. Make sure you know how to plug into your calculator logs. Remember to take the negative of it. And what do you get? 11.8. Everybody get that? 11.8. If the pH is 11.8, what must the pOH be? You see why? Could be 14 minus 11.8, right? Is that fun or what?
That is the most fun.
Now I have the homework for this one too. I believe it's, I don't know if it's the same one that's there. Let me see. Have we got that copy? Hurry up. Okay. There's the homework. Yeah, it's the same numbers, right?
You don't know why we do that, Josh.
Copy that down. That's the homework.